right? But I also have some initial amount of B loaded, initial amount of C, initial amount of D. Is there anything else that might be in your reactor? Solvent, inerts.
Catalyst.
Yeah, catalyst can be in there, but we don't really think about number of moles of catalyst, but it's obviously not changing. But yeah, you have inerts, right? So by the time you guys get to chapter 5, the problems, pretty much all of them are going to deal with inerts, because it's very common to have inerts flowing through a reactor. Why? Can keep the heat down, that's right. It can act as a way to sort of separate out, to distribute out the heat. Anything else?
Flammability.
Flowing out, like into gas.
To keep what?
Like the reactants of products going into gas phase. Maybe?
I mean, yeah, I could see that. Flammability, sure. If you have a mixture of, for instance, oxygen and methane, you might want to flow a lot of inerts so that you don't get into the flammable mixture of oxygen and methane.
Is there a way to control rates?
It can be, because again, rates depend on concentrations.
Can it help with separation afterwards?
Maybe. It would depend on what you're doing, but there are systems that become biphasic, or really are always operated biphasic. So you might have a liquid system where you've got an aqueous phase and an organic phase. The organic products that you make go into the organic phase while still in the reactor. So it'll automatically help you partition your products.
Physical properties?
It can be, yeah. So there's tons of reasons. Another one you guys didn't name is, what if I wanted to be at really, really low pressures? Would I want to run the reactor under vacuum if I want low pressures of my reactants? No, I just feed an inert, right? So that's a way that I can run at atmospheric total pressure, but the pressure of my reactant might be like 1 kilopascal, because maybe it's a toxic species, right? And I don't want to have large concentrations of a toxic species in my plant. I want to dilute it, and it's not just for a kinetic purpose. Somebody mentioned that earlier. I might want it to go faster, but it just might be unsafe to have, for instance, nitric oxide or something at a high concentration, which kills people at like 15 ppm. So if I wanted to do that in my lab, I would buy a tank where it's already like 1 part per million or 10 parts per million or something like that. Okay, so all of this is at time 0, right? And if we go to some time greater than 0, then we have some conversion that occurs. And as a reminder, A is the basis for that conversion. So how many moles of A are consumed mathematically? No. NaO times X. Right? That's how many are consumed. That's the definition of conversion, is it's moles consumed divided by moles fed. Well, here's moles fed times conversion means moles consumed. All right, so we're going to set up a table over here, and I'm going to try to leave alone because we're going to alter it a few times today, so I don't want to rewrite it 10 times. And this table's in the book. I think it's 4:1. So what do I put here for initial number of moles?
NaO.
What's the change for A? Na0 times X. What about B? Yeah, sorry, this change should be negative, right? Because we're not talking about number consumed. That's what I asked earlier, but change negative. And yeah, you got it. B over A, because remember that's what we did here. Is we first divided through by A so that when we write conversion, this is 1, right? We're saying conversion for the reaction as written, but what Fogler usually does, or instructs you guys to do, is divide through by whatever that first coefficient is. So it's B over A times NaO times X. Why is it NaO and not NBO? Yeah.
Because our basis is in Na.
Again, the basis for your conversion is on species A. So that's what shows up here. What about C?
C over A and A, right?
Yeah, positive C. What about the inert? Yeah, that's why we call it inert. Okay, what's left? NaO minus NaOX, right? Everybody see that? I'll fill it in, but this is pretty simple, right? NBO minus B over A, NaO, X. So many devices in here. I feel like I'm misusing the room. All right, let's add things up. What do we get here? Just the sum of NiO, right? Or we've been using J, so continue that. That we're going to call NTO. If you see that big T in the book or in a problem or something, that's total, all right? Not temperature. That's big T. Not enough words. We won't write down the sum of the change. And I'm going to put it up here just because I think it's a little bit easier to read. But this sum is in T, right, at some time, sum of Nj, which is equal to the sum. He went ahead and substituted it in, so we will too. NTO, the sum of all the initials, plus E over A plus C over A plus, I'm going to run out of room. Everybody see that? Everybody knows that's the sum. It goes over there in the corner, right? When you're making your nice, pretty table. Why is this a 1? It's A over A, right? Things like that annoy me. I'd almost rather they just put A over A. Because it seems like there's some trickiness about it. Like, oh, that's 1. I've got to remember that that's 1. No, it's just all the stoichiometric coefficients divided by 1. Yes. So we're going to define something that helps us out a little bit. We're going to say this is delta, lowercase delta. Okay? Now that is also, if you do the math, simply the sum of the stoichiometric coefficients. Because notice that if I multiply through by A, right, it's just D plus C minus B minus A. Well, that's just the sum of the stoichiometric coefficients. Okay? So you don't have to divide through by A in order to calculate delta. It'll work out the same.
So is NaOX the extent of reaction?
No. NaOX is the number of initial moles of A.
Well, I was just wondering because if you compare it to the extent of reaction equation, it would line up immediately that NaOX is equal.
Oh, sorry. You said NaOX. Yeah. When you say NaOX, I'm thinking one thing. Yeah, NaO times X is extent.
Okay.
So if we come back to this formula, we can also write it just in a more condensed way using our new symbol Yeah.
So would delta be little a plus, or C plus D minus little a minus B, or would it be that times initial moles?
Little a is just this. I mean, sorry, little delta is just this.
Okay.
It's just this part right here. So I mean, look at the substitution I just made,
Okay.
and hopefully that'll make it clear. It's just the sum of the stoichiometric coefficients. So in words, what is it, right? It's how many moles are produced for every mole of A consumed, right? If I consume 1 mole of A, do I produce more moles than I start with? Do I consume more moles than I start with? It obviously depends on the reaction, right? Depends upon the stoichiometry. But some reactions produce moles, some consume moles, some don't change the number of moles at all. Those are not the ones you're going to get on a test. Where would the fun in that be? Okay, so that's the reaction. For convenience, we're going to define something else, and then we're going to change our table over there using this new big theta J is equal to NJO over NAO, yeah.
Is that the sum of the stoichiometric coefficients supposed to be over A?
So delta is equal to D over A plus,
But when you make it equal to the B symbol,
Yeah.
right, but what I'm saying is, the notes don't have it written that way, so I'm just double checking. I think it's the same, but. Yeah, I guess the A would come out front, yeah. Okay, so again, for convenience, we're going to define this large theta as the number of moles of that species divided, yeah.
No, that's not right, because you define the stoichiometric coefficients to a problem.
Oh,
So for the second part, you change the moles to over A, so it wouldn't be, because it's based on how you define the equation.
yeah, you're right. Yeah, because, again, if you guys didn't get that, I erased it, or no, I didn't. This is now the stoichiometric coefficient on B.
Oh, okay, gotcha.
Yeah, and that makes sense, because when you're solving for conversion, again, you want this first species, whatever you're basing conversion on, you want it to have a stoichiometric coefficient of 1. So again, the first thing that you want to do, if I give you a problem and it's 2A goes to B, is what? A goes to 1/2 B. That's right. Yeah, I was surprised. I wouldn't think there'd be a problem in the notes. All right. These are pretty old, so should have been fixed by now. Okay, so if we set this up, then again, we're going to change that table over there, but we'll pull how we're going to change it here. So NA is equal to NAO times 1 minus X, right? That's the same as that. Everybody see that? It's the same. I just factored out NAO. NB, now in terms of NAO, notice over there it's NBO, right? We want to put it in terms of NAO, just again, out of convenience. And so now what we do is we have big theta B times B over A times X. Okay? And of course you get the same thing for C and D. I'll put C on the board because there's one difference, which is that it's plus C over A, because it's a product. So again, we want it in terms of conversion.
It's an NA over O, right? Or NA over.
Yeah. So we have now number of moles in terms of conversion, but what did we want? What did we start the class with? We want to get concentrations in terms of conversion, right? So how do I go from number of moles to concentration?
Divided by volume.
Right, concentration is equal to number of moles divided by the volume. So I can come back here, and now I can write this in terms of that. So I can come back, and I'm going to say that the concentration of A is equal to NaO over V. Right? And we'll put up the concentration of C as well as a second example, but obviously you're going to get 4 equations. Concentration of C is NaO times theta C plus C over A times X. Right? Am I done? Do I now have a term that gives me concentrations as a function of conversion? Kind of. What about volume, though? Can volume change with conversion? Depends on how I'm performing the reaction, but in general, yes, right? In general, yes. So volume is a function of conversion. So I've gotten the conversion out of my number of moles, right? I've gotten rid of the number of moles of that species, and now I have it in terms of conversion and the number of moles of one species, right? So that simplifies things. I only have to worry about number of moles of one species. But I've still got volume, which can change with conversion. Yeah.
I feel like we've all done this before, and for me, I feel like this is like way more complicated than the way we've done it like in past classes. I was just wondering if there's like a reason for that.
I don't know what you did in past classes, so I mean, I don't know.
I don't know. I just feel like extensive reaction, like in prior classes, were like more straightforward. Maybe it's just like.
Oh,
all
extensive
the-
reactions. Yeah, but they're.
Is it because we're trying to relate it to like concentration?
It's
volume,
because you're
or-
trying to relate it to rate equations. Yeah, extensive reactions. You guys never learned how to write a rate equation in terms of extensive reactions. Certainly not for anything complex. This class, we're going to do that, right? So we need to get things in terms of concentrations and conversions, not extents. And then on top of that, what else can be changing? The volume can be changing, the temperature can be changing. Yeah, you might have done reactor systems before in material balances, but they were very simple reactors. Okay, so the concentration I can write in terms of number of moles in fed of A, conversion, and volume. But again, volume generically can be a function of conversion. So obviously, if I have constant volume, then we're going to say volume is equal to V naught, just initial volume. And all we have to do is come over here now and simply change those. And so we can also write it as we have before. CaO, the initial concentration, times 1 minus X. And this is CaO times, again, we have that theta B. Sorry. Yeah.
Wouldn't volume usually be constant in a reactor?
So we're going to talk about flow systems, but even in a batch reactor, volume is not